So far we have been talking about different ways of representing integers. We know how to represent both positive and negative integers, and we sort of have a handle for how we could get those represented inside a computer. But remember Kroneker's quote, right? All else is the work of man. Clearly there are things beyond the integers, right? And an example of that would be the constant pi, right? 3.1415. Now how do I go about representing a number like that inside a computer, right? And now you might start to think of ways. Essentially what one way of looking at it might be, hey, why don't I break this up into two parts and say that this 3 before the decimal point is an integer part, and whatever comes after this decimal point is what I call my fractional bits. One possibility is just take them as two separate numbers and represent them, right? Perfectly valid, right? It can be done, right? And there are both pros and cons of that approach. One of the biggest sort of cons or disadvantages of that approach is of course going to be that actually doing arithmetic with numbers where you have taken the two different parts and stored them separately is going to become harder. There are ways of getting around it, but maybe there are other ways as well by which you can go about representing numbers like this. Now another number, which in this case the actual speed of light is some 299,000 something meters per second, right? Or rather it's very close to 3 into 10 power 8 meters per second, right? So what is this notation exactly, right? What it's saying is that it has this number out here 3, which indicates the magnitude of the significant digits, so to say, right? But the actual magnitude of the number, how big it is indicated by this part out here, the 10 power 8. That is what gives it its size, right? 3 by itself is a relatively small number, but when I suffix it with this into 10 power 8, suddenly it becomes a large number, right? This is usually what we call the scientific notation. There are two ways of doing it. One is that you could have just written this entire number out as 3 followed by 8 zeros, or we could choose to say that I'm going to use this notation, which is the scientific notation, where I essentially say there are some significant digits that give you the range in which the number is, but the actual magnitude is going to be conveyed by this multiplicative factor 10 power 8. That is taken even further, for example with things like Boltzmann's constant, where I have to represent it as 1.38 into 10 power minus 23. There is really no meaningful way to represent this by writing it out as a decimal number, right? I would end up with like 20 zeros after the decimal point, 23 zeros, which sort of doesn't convey what the number is supposed to be. It's very hard to understand that value. So this, what we call scientific notation, is actually a shorthand which once again is easy for humans to understand, but it turns out to be also a very good clue about how we could go about representing these things for computers. So if I do want to represent real valued numbers, like I said, one possibility would be to take the integer and the fraction and just treat them as separate numbers. The other possibility would be to say that I will take a regular number, let's say 16 bits, and I'll multiply it by a scaling factor, which in this case is 2 power minus 8. Okay. What does that mean? It means that the number 1, for example, right, would essentially correspond to the number 1 by 2 power 8, or the number 35 would correspond to 35 by 2 power 8, right? Both of these are, in other words, fractional values less than 1. But what about a number like 10,000? This would correspond to 10,000 by 256. An improper fraction, but still a good way of essentially representing a real valued number. Effectively, in other words, what we are saying is we are going to represent fractions, right, with a fixed scaling factor out here. Now, is that necessarily the only way of doing things? it is one way, and it is in fact used in a lot of different contexts. This is what is called fixed point notation, right? Not many sort of general purpose computers use this. There is nothing preventing you from writing programs inside your computer that make use of fixed point. Why? Because after all that fixed point is another convention, right? It's not as though the scale factor is actually physically present somewhere inside the computer. It's just that I have decided that this particular set of values, these 16 bits, is to be interpreted as a number that first you convert it to its equivalent value and then you scale it by the factor 2 power minus 8. Does the computer actually do any of this? No, the computer just stores 16 bits and I perform all my computations with it. But when I interpret the values, I need to keep that in mind, that this was actually a number in this fixed point notation with this particular scale factor. So as long as I can take that into account, right, and I follow this convention, I can represent a lot of fractions, right, and a lot of what I want out of real valued numbers can be represented in this way. But in practice, the other approach that is followed is usually the scientific notation, where what we say is that the number effectively carries the scale factor along with it. This is like saying that the number is 3 into 10 power 8. The into 10 power 8 is very much part of the number itself. The same way 1.38 into 10 power minus 23, the into 10 power minus 23 is very much part of that number. Boltzmann's constant without that scaling factor doesn't make sense. But each of those numbers, 3 into 10 power 8 and 1.38 into 10 power minus 23, they have their own scaling factors which they carry along with them, right? Once again, convention, what we do for example is to say that if I have a 32-bit value, I'll take the first 1 bit and say that this represents whether the number has a sign or not. I'll take the next 8 bits and I'll call it the exponent. This is the equivalent of the 10 power 8 or the 10 power minus 23, except that it will be 2 power something. And this part is what I call the actual value or the mantissa, the remaining bits, right? The equivalent of the 3 or the 1.38, right? Why these particular choices? That is a set of choices that were made as part of a standardization process. It is very much a convention, right? But it is a very nicely standardized convention which is now referred to as floating point notation. Okay. So once again, if you really want to dig deeper into floating point, yes, there is a lot that you need to understand about the different ways by which they are represented, how they are implemented, what are the implications in terms of accuracy and so on. But right now what you as a programmer need to know is that it basically is a standard convention which is accepted by most CPUs. You could use what is called single precision floating point representation. And what does that mean? Remember that we talked about the smallest and largest numbers that can be represented using integers. The same way you can talk about numbers like that for floating point. The interesting thing is, look at these, I am just talking about the positive numbers alone that can be represented in floating point. Just with a 32-bit value, I can actually represent numbers all the way from 10 power minus 38, really small quantities, to 10 power plus 38, really large quantities, right? So this notation, for example, could handle both Boltzmann's constant and Avogadro's constant because it has the range of values required in order to represent them. This ratio between the largest and smallest is usually called the dynamic range. In this case, I have a dynamic range of 10 to the power of 76. The smallest positive value versus the largest positive value differ by that much in orders of magnitude, right? But even that is not good enough for certain types of scientific computing, right? Maybe climate simulations or some very specific kinds of computations. For those, people tend to use double precision numbers, which are essentially the same kind of sign, exponent, mantissa, but with 64-bit numbers, which effectively gives us a much expanded range, 10 power minus 300 to 10 power plus 300. Right? There is a quad precision which goes with 128 bits, but beyond a point there are diminishing returns, right? And it all depends on what you are trying to do, and probably if you are dealing with very large or very small numbers, maybe some other kind of scaling should be used in order to make them more meaningful. Now, part of the reason why double precision is important is not just to do with the fact that I want very large numbers, it is also the fact that I don't want a lot of errors to creep in, because one of the important points that happens when I am working with these floating point numbers is how exactly do I round the numbers off, because unlike integers, right, where if I know exactly how many numbers are there within 32 bits, anything else it overflows. Floating point tries to represent more and more numbers, but what that means is it starts to round off values, and potentially errors could accumulate over time. So this kind of rounding and error analysis is something that as a programmer, especially if you start looking at numerical programs, you need to be at least aware of the fact that floating point can in turn have errors, right? These are not sort of the abstract numbers that we are dealing with over here, which we deal with in math. These are very physical numbers with a finite representation, right? In pure math, in principle, there are an infinite number of values between any two numbers. Inside a computer, no, there are only a finite set of values between any two numbers. Right? So those kind of things need to be sort of taken into account when you are actually trying to do certain kinds of computations. For most practical purposes, you don't care. And for those of you who are interested in machine learning applications and so on, you might have recently come across a lot of hype and buzz around what's called half precision, right? Because some of the big sort of CPU manufacturers or GPU graphics manufacturers are claiming that they can implement half precision. Not claiming, they are implementing half precision. And the reason why that works is there are a lot of applications where even this kind of range of numbers or the kind of precision that we get with these mantisas is not really required, right? We can get by with a lot less. Machine learning applications tend to be very forgiving of such approximations, and they are a good candidate for even fewer bits. Why would I want fewer bits? Going all the way back to our the fact that we have physical circuits, the smaller the circuit, in general the faster it will run. Okay, so once again, at the end of the day, these are engineering trade-offs. We have made certain decisions based on what is available to us. As a programmer, you need to be aware of the implications of floating point, but right now you could probably just get by saying, okay, these are numbers. Why this becomes relevant for C programming is because float and double are two of the data types that we will be encountering very soon when we start actually writing programs.